พื้นฐาน Hear me? Okay, thank you. Good morning, good afternoon, everyone. Yeah, it's our great honors to have incredible VIP here today. Yeah, and actually, he has a very long title. So, Professor Honoris Causa Doctor England and habilitation. Yeah, Professor Eugen Zazarsky from the Technical University Dresden. Yeah. And actually, he have lots of the honor and award. So of the several page. So I don't have the time to let you know the detail. But anyway, it's very fortunate you can Google his name, or you can use the Wikipedia or even the ChatGPT. You can see all the detail of the award and the honor. Yeah. For example, Dennis Gabor Award or something like that. Yeah. Okay. It's so. But anyway, today the most wonderful event is Professor Zazarsky is here to deliver an plenary talk to share with all of you. So let's beat your hand to welcome his talk.
Ni hao. Good afternoon, Zhechen, for the kind introduction, the kind invitation. And on behalf of my group and the cooperation partners, actually it's a really great honor to share results on information photonics. Actually, information photonics is based also on AI. And we will outline today actually the intelligent photonics for information processing in biomedical imaging and fiber communication. I will highlight that right now you can really do both. You can do data-driven algorithm, deep learning, that's one leg, and the other leg is physical simulations, actually really to have a theory and simulation to get a view to the black box of deep learning, to explain, to have a generalization, to scale. And I will highlight physics in deep learning for 3 examples. It's everywhere the same method, but different applications. So this means there is endomicroscopy for biomedicine, to look in a 3-dimensional way into the body, metaverse, and also secure data transmission. And the good news is you can write 3 project proposals and you get 3 times money. All right, so if actually we are really here in such a wonderful country, I have to show also some really some pictures, some photos, and that's really photos from actually meetings in Munich, in San Diego, and in San Diego there was also an award for Taiwan, and this was actually the student chapter. And I really appreciate my hosts sitting there, really to organize everything. And actually yesterday I have met the student chapter. And this is of course for me a very great opportunity to be here at this wonderful conference, but also to see a little bit around and to meet also the next generation and other universities. Because my university is already in Taiwan. We have actually a trans-campus here, and the trans-campus is looking for people who wants to have money. Because the money is already there for international cooperation, but the links are not so really clear. Of course, there's TSMC. TSMC is also in my city, and therefore there is a close link, but there are further cooperation possible. And therefore, it's really for me a great honor and a great opportunity to be here. Yeah, this is also for another visit, and also really great food and really great meetings. If you look back, then not so long ago actually there was industrial revolution, the steam machine. Automation came, and then it was thought the third industrial revolution, the information area, what will last. But we are living now in a very exciting time. We are living now in intelligence revolution, AI revolution. And actually, if you look really to these photos, then you can imagine how fast is the progress, how fast is really the revolution happening. What can we do if we combine photonics with AI? We can do both. We can say AI is improving photonics. That's mainly, is this working? That's mainly my talk today, but we are working also on the other side to use photonics to improve AI, because AI has really a crossing of the energy which is needed for AI with all electrical energy which is generated. And this crossing point is coming closer and closer to us, because AI is really growing exponentially. And the exponent is also really growing. Therefore, you have to do something, and photonics is also able to improve AI. But this is maybe another talk. Yeah, and actually, that's has started in the 1940s, 1990s. I have done already AI, and I have given it up because it was an AI winter season. And then it came up with deep learning, and now we have really deep holography, where we combine really holography with AI, and it's not only exciting and not only unique advantages are there, you can transfer more and more into really crucial applications. So that's an overview of that's an overview of my lab, where we have 5 groups, and I will speak today about 3 applications of physics-informed deep learning. That's biomedical applications, augmented reality, so metaverse, and also a little bit really fiber communication. Dimitri Saltis is a very good friend of me, and he has said fibers were only good for energy transportation if you use thick fibers, multimode fibers, because you have scattering there. But information photonics has changed the paradigm. Now you can do really 3-dimensional imaging for an endoscope based on a multimode fiber, and I will speak really about a new application where we use AI for driving secure transmission through fibers. And yeah, that's a project prize which we have won a couple of weeks ago, where we exactly do physics-informed deep learning with GPUs, without GPUs, really by photonics, and really with driving security and also quantum technology. I'm coming from a country which is not around the corner. It's really long flight, and this is the city is Dresden, 2 hours south of Berlin. And we had really the honor to organize, based on my position as a vice president of International Commission for Optics, a world congress. And several colleagues sitting here were there, and this was a congress during pandemic. It was shifted 2 times, finally happened 2022, and we have had 55 countries and 3 Nobel Prize winners at one conference. And you can see here they were really in vivo there, not by Zoom. Yeah, I want to start with physics-informed deep learning in the way that I will present a new kind of endoscope for 3D imaging, lensless, real-time, means video rate, and we have really very special features where only physics-informed neural networks can really advance the system. We really image through a kind of diffuser. You take a piece of paper, and my hypothesis is this piece of paper, which is very, very thin, that you can look a little bit through it, but all is really scrambled because there is this huge scattering. My hypothesis is this diffuser is better than the best objective you can realize. You can, of course, realize for ASML really huge optics with mirrors or also with lenses, but you can't really see through a scattering media. And my hypothesis is you can do three-dimensional imaging with better space bandwidth product and other key parameters than with a lens system. Yeah, I will speak actually really using diffusers for endoscopy. This is supported by our Center on Biomedical Computational Laser Systems. And key players where I have to acknowledge now are here Tom Glosemeyer mainly. Yeah, if you actually look to applications of endoscopes, then it's huge variation. It is of course important for cancer diagnostics, for several other fields, also for dentists. They want to have endoscopes and the root channel. You can go into the heart or into veins, the arteries, but actually there is one special surgery where at the moment really the medical doctors have no progress since more than 20 to 30 years. And they have asked us, can you help us based on information photonics? The task is as follows. You have by other methods, for example by X-ray or PET, an area under suspicion that there could be a tumor. Then you have a biopsy needle, and actually right now you cut tissue. This tissue is then at a cover slice and very thin below a microscope. And actually you want to know now which kind of tissue do you have. Therefore you use chemical substances. And then you have several medical doctors and they are looking to this tissue. This can take 1 week actually. And after this week you can make a new surgery. The idea is really to do an in situ real-time diagnostics without chemical substances. By AI you can do virtual scanning and with a very tiny endoscope. Yeah, this was the beginning of a discussion with medical doctors from our hospital, and then we have looked what is the state of the art on 2D imaging. Also for 2D imaging you don't find really very small endoscopes. This is here lens-based, that's camera, that's a scanner, that's fiber-based. All is larger than 1 millimeter. Often it's 5 millimeters. 5 millimeters is already challenging. And of course it's only two-dimensional, and therefore we have thought, can we overcome these limitations by information photonics? The idea is really shown here. You take really the piece of paper, and fiber endoscope without lenses, 10,000 fibers are there, and on the other side you have of course a standard optical system. You illuminate by a laser through the endoscope and you get here an image. Of course it's not paper, it's a Scotch tape, also cheap. Simply a Scotch tape, standard camera, standard coherent fiber bundle with 10,000 single mode fibers, that's it. Yeah, we have read it's really possible to realize a diffuser microscope, a diffuser camera. And then we have said, why not to try to realize a keyhole access diffuser endoscope? Yeah, that's actually the idea. You have here an illumination of cancer tissue. You see here label 3, several areas where you have autofluorescence. This light is coming back, going through this diffuser, and is of course scattered in several directions. Then it hits really the fiber. It's guided through this endoscope, and here you have the camera image. How good is the camera image? You can't speak really about a camera image. You see only speckles here, and you have only 10,000 pixels. How to see exactly such a reconstruction? That's the scientific question. And actually you can see here we have a task to do encoding by the Scotch tape. So the scattering is of course different if you have different distance from the fluorescent dyes. If you have really lateral changes, also you see a different speckle pattern. And then you should do an encoding of such an image. All right. We start now with theory. We start with simply one point. One point is scattered here at the diffuser, and then you have a speckle pattern, and that's 1 point spread function. You can do this for any point, and then you have the fiber input. The fiber has only 10,000 cores, therefore you have a pixelation, and finally it looks like it was shown. That's really results from the experiment. Okay, what is the state of the art? We can look to Berkeley 2018. That's the diffuser camera. And they have said Garchbeck-Sexton is of course able to do an inversion, right? You can do phase retrieval. Here you can modify this, and then you have a method, really deterministic method, really to reconstruct really this beautiful plant here. And if you look to really the method, then you can say here you have no explainability problems, no black box. It's deterministic technique, but it's pretty slow, very slow. And it works with 40 million pixels. Can you do now keyhole access inside of your brain, really with a very thin fiber? Is this also working? All right, we have checked this, and we have seen no. With 10,000 pixels, no chance. Therefore, we have developed our own network, and this is based on a single layer perceptron and a NtuEE. The NtuEE was developed in Germany 2015, and it's good for segmentation. But first, you have really to evaluate really the speckle pattern, and this is done by the single layer perceptron. How good is it? We can look to that. It's pretty fast, at least 100 times faster. And we have seen training can take 1 day. And we have problems with generalization, explainability, and overfitting. All right, first approach, we will look to some results of simulation. Here you can see really the algorithm, the deterministic algorithm, working for a microscope, working for the diffuser camera, not for keyhole access with an endoscope. The combination of single layer perceptron and NtuEE is here the winner. But is it also good enough for an application? No. It's fast. You can see here a running man in front of really the diffuser, scattered by the diffuser. Intensity is really propagating through the cable, through the fiber cable, and then we see such an camera image. AI is really smart. So I'm not able to see here a running man. That's here the ground truth, and it's really close to that. So really a surprise for me how good is this running, but you should not work for your own success. You should work for the success of your cooperation partners. We want to transfer this to a clinic, and they are saying, no, that's not good. Here you can see the resolution is not really high. We want to have 1 micron. Do you have 1 micron? No, we have 5 micron. All right, so then we have started with a new project, but I will summarize. We have now a 3D video rate system with keyhole access, no lenses anymore, and I think anybody can realize this. You have here the Scotch tape, diffuser tape, the fiber, this is only a spacer, a laser for really stimulating fluorescence, and a camera. That's it. But how to make it really working? Then you need the decoding. You do here in encoding, but how to do the decoding? That's really the innovation. All right, a little bit theory. Actually, we can see here the field of view larger with the diffuser. Lateral resolution depends on the distance, but space bandwidth product could be 1 magnitude higher compared to lenses. What is now the approach? The approach is actually the unit with data-driven to combine it with a deconvolution network. And that's actually a learned multi-Wiener deconvolution. How is this working? Here is the camera image. We go through the system, then we have here the output, we compare it with the ground truth. The ground truth is at the training coming from a DMD. And then we have a loss function, and we go back to train the unit, so the deep learning, and then we have here also regularization parameters and spatially varying point spread functions for different distances. How good is it? It's the winner. It's the winner in SNR, in contrast, structural similarity index measurement, in correlation coefficient, and it's also a little bit smaller. We have not to train so much. Here you can see how good it's working. 3 different objects, very similar speckle pattern, and here you can see the reconstruction. All right, so can we do more than 2D imaging? Of course. It's 3D encoded, therefore we can reconstruct in 3D. 500 microns distance to 850 microns distance, and that's really the contrast here. Okay, I am summarizing this first point because time is running, and you can see here further ideas. What can you do with really data-driven and simulation-based? So how can you really make a progress there? And we think we should buy a Scotch tape for the endoscope. We should print an meta surface, and that's really the plan here, to do an holistic optimization of the system. In conclusion, we have a pretty easy optical system. We use a diffuser instead of lenses, therefore we can do real-time 3D imaging. The challenge is actually here how to do really the reconstruction. And at the moment, really the resolution is not good enough for applications. That's a new project where we want to work on. I'm coming fastly to the second topic, and this is really the same. It's also the multi-Wiener net, but now for metaverse. This is the task. You have here the retina. You see an object and you want to realize a see-through camera with a waveguide. But actually you have really strong aberrations there, because the light is coming only from one point here, but going to several points here at the camera. What is the state of the art? That's the ground truth. Camera image, highly distorted. It's similar to the Scotch tape. Here is the reconstruction by deterministic techniques, and that's the ViNAnet. It's trained in the same way like before. Here you can see how we have done this with our cooperation partners with an OLED display, and then you have here different images, and we have trained really the ViNAnet with regularization parameters, and instead of 15 minutes for one image to undistort this by deterministic algorithms, we have now 250 milliseconds, and you can see here image quality is much more better. I will skip this because of time. So it means we have actually 4,000 times faster reconstruction and higher SNR, higher contrast. All right, in conclusion, I think the time is right to do not only data-driven algorithms, to combine this with the skills, with the knowledge about the physical system, to try to combine this, and we have done it with an e-convolution network. What else can you do? Briefly, in the last minutes, I will speak about information technology for internet. And you can see here everywhere exponential curves, so you have to do something there. That's Keck's law, and important for cars, for robots, public health. All is going up, but what is the next technology? And I will speak in the last minutes about the same idea to do physics-informed neural networks for internet, for multimode fibers. You can see here multimode fibers for computing, fiber lasers, endoscopy, and also for secure communication. The message is, like at the diffuser, where we have seen, it's really possible to get better 3D imaging with a diffuser compared to lenses. Here to do the same, that AI is really improving the transmission of data, of information through fibers. That's happening at the fiber. It's the same like at the diffuser. You have here a number and speckles are coming out. But you can do a phase retrieval, and a lot of papers are existing there. Yeah, we have actually started with this topic about 10 years ago, and then we have seen a lot of papers are on holography, but holography is not really working if the fibers are very, very long, because you need then also a very long reference fiber, and the length is changing. And therefore the idea was actually, besides holography and iteration-based techniques, to use AI. Okay, I will skip this. So that's here holography with different SLMs and really cameras. And we have then started to get rid of this reference and really to work with a phase retrieval of the intensity. Okay, so you capture really the intensity after the fiber propagation, and then you will retrieve amplitude and phase. So this has worked with 12 hidden layers with 3 to 10 modes. Here we have 121 layers already, and that's a further message of this talk. AI is really not easy to scale. You have also, if you increase the number of modes, you have an exponential growth of the number of layers. What is the next? It's ChatGPT. And ChatGPT is needing more power, more training time, and so on. You can't scale this really so easily, because now we have 33 hours training time already. And the number of modes is 23. We want to have much more. What is the solution? To include the physical knowledge about the fiber. And that's actually here done. Here is the physical model. It's the same like before. Deep learning combined with physics. And how good is it? We have now a world record over 1,000 modes decomposed. And this is because we combine really at our technique, at our FISMONet, really the physical knowledge. We have increased this furthermore to over 5,000 modes. You have seen scalability is really very challenging, only with the data-driven. Now you take physics informed together, and you can increase this to several magnitudes higher numbers. So actually that's our suggestion. It's referenceless, its scalability is there, robustness. What is missing? Unfortunately, this is not fast. Okay, and that's really my last slides. We have then said we have here data-driven supervised learning. We were moving to unsupervised learning. Of course, here we have the physical model inside, that's physics informed, but time consuming. Can we make a compromise? That's really my last suggestion for today, to do hybrid learning. All right, and hybrid learning is several magnitudes faster, that really the fiber can be also bended, and we learn about the mode decomposition. That's of course crucial. So that's really the summary. We have here physics and data. This was the first approach for the multimode fibers. I have then briefly outlined physics in loss, and there is also a further method, but this is maybe a talk next year. And yeah, that's actually what we are doing here with really the physics-informed deep learning, where really we can capture the data, the scattering processes, and then we can explore this for secure communication. In conclusion, it was really a great pleasure to speak here at this famous conference, Information Photonics and 3D systems on physics-informed deep learning, to really merge physical knowledge with data-driven techniques for endoscopy with diffusers, for augmented reality with a see-through camera, and the last minutes were really only a glimpse of what can we do really with fiber, multimode fibers for transmission of data information. And in a nutshell, I can say we are really in a very promising area where physics, so also holography, is combined with AI, and this opens really new applications for biomedicine, for metaverse, and also internet. I thank the group, your kind invitation, and thanks for listening.
Can you have a quickly question? Actually, I have many questions. Because the first question is a few years we work on the diffusing camera, the diffuser for the image, or two-dimensional, three-dimensional image reconstruction. But finally we find, but we don't continue the work. One of the reasons is the information capacity. If you can reconstruct, diffuse the image in one plane, maybe you have to sacrifice something in that plane. For example, resolution, time, or energy, something like that. So, what's your comment on that information capacity or channel capacity?
My comment is these problems can be solved now because first the energy problem is existing because the scattering is in going to angles where you have no detection. By matter surfaces you can change this because where you can really design in which direction the energy is going. Of course, the scattering process is at the moment so complicated that we can't really image with high enough resolution. Signal to noise ratio is another issue, but actually we illuminate here with a laser only fluorescent fluorescent proteins. It's a different application. So my message is the diffuser endoscope is only working for sparse objects, not really for something where you want to have, for example, such an photo of this card. When it's not working, you need really sparse objects. If you have a sparse object, you can also increase really the spatial resolution, and we think 1 micron is possible. So at the moment it's 2 to 5 microns laterally and 50 microns axially. So laterally we have already a resolution of one cell. It's not good enough for virtual staining, but it can be improved. That's our hope. Yeah. 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 Okay. Yeah.
Okay, so please stay your seat and then we have brief focus. So, please thank Professor.
没有，这个是捐你的。Thank you.
这里拍不到吗？哎，后面的会看不掉。Yeah, so then we'll cut So you are going to come closer.
Come closer.
Yeah, so 后面
你试过了吗？可以了吗？前面要拍得到。对，OK。前面要拍得到。因为会被划。So, yeah, because the maybe cut out. 那现在的 view 是多少？你要 copy 一下。
Okay, let's take a photo now. Okay, 3, 2, 1. Okay, thank you everyone. Oh, one more? Okay, okay. Okay, that's the photo. Yeah, okay. 3, 2, 1. Okay, thank you everyone.
就是要分2个 session。
对。那我叫一下。The next session will begin at 3 p.m. May I kindly ask the session chair, Professor Hirotsuku Yamamoto and Dr. Zhang Quanzhong, to come to the front to collect the materials for the session. And the invited speaker, Dr. Jingsu Zhang, to upload the presentation files. Thank you. Oh, okay. Oh yeah. Okay, this is the information for the session. Thank you.
How did use it?
要上去。
应该自己会上。Dr. Jingsu Zhang.
Yeah.
两位都来。
没有哎。
结果不是他哎，就是他们两个。
对啊，可是我说这个。对啊。
军书卷。
对啊。It's Dr. Jingsu Zhang. Oh, okay. Sorry. Okay.
前面。
哦。
OK。
有这个。
专业就这样子啊，所以看你。
Hi everyone, welcome to analyst section afternoon. So I think we have a very interesting and exciting invited talk given by Dr. Jin Shu-jian coming from the Korea Electronics Technology Institute. So Dr. Jin is right now, he is in interesting area including optics, holography, 3D display, and deep learning. And he also been served as many high respect journal reviewers. So today his topic is about application for optical technology for extended reality. So let's welcome for Mr. Jin.
Good afternoon, ladies and gentlemen. It is my great honor to inviting me for the 3DSA 2025 right after the plenary session. And my title is Applications of Optical Technologies for Extended Reality. And I'm from South Korea, and my organization is Korea Electronic Technology Institute, called KETI, and I'm at the Hologram Research Center. Okay, let's start the presentation. So the title is Application of the Extended Reality. So I think this is the very representative image of the extended reality, and many of you already saw images. And I noticed that the 2 points. The 1 point is that not every single, just most of the image of the extended reality they wearing a headset, like head-mounted displays, or Apple Vision Pro or MetaQuest or Microsoft HoloLens or something like that. And another point is there is always avatars or digital humans. And these are the digital humans in Korean, like a very favorite singer, IU, in the Southern Tech game. And this picture is a K-pop idol aespa, my favorite. And so there are a lot of the avatars are represented for the extended reality. So in KETI Hologram Research Center, I conducted 2 major projects for extended reality. They have big accordance with optics. The first thing is augmented reality HMD for the navigation, like a mobile grab or something like that. And another thing is generating photorealistic avatar with 3D face scanning technology. So I will introduce these 2 projects at this presentation time. So let's start with the first project. And these are the AR optics in KETI when we developed that. we developed the various kind of AR optics, such as a waveguide, refractive time, combining the multiple pressure mirrors like this. So there should be a waveguide in the side of the AR glasses, and you can see the very clear image with the waveguide system. But it has a very weak and it has some thickness. So we developed AR optics with a projection time with a holographic lens using holographic optical element technology. So by using the holographic lens, the thickness should be like 100 micrometer, like a film type thickness. By projecting some images to the holographic lens type AR lens, you can see the very clear and transparent and pattern and images with the holographic lens. And so the further research of the holographic lens technology is using a holographic optical element printer. The holographic optical element printing technique is kind of design the holographic optical element with the digitally and printing the digital pattern at the holographic film. So when you make a ordinary or a conventional HOE, you need to design and you have to fabricate the original master optical element. So it is very hard and it takes a very cost. But by using holographic printing method, you design and just calculate the pattern with the hologram and just print it. Then you can make the customized holographic optical element. And another benefit of the printing technique is you can print the optical element that it is hard to fabricate by the glass or something like that. So you can like a multifunction or very, very complicated freeform lens or something like that. So this is the benefits of the holographic optical element printing technique. So we have a digital HOE printing setup like this, and we have we build a software for the control the each hoggers. Based on the HOE technique and the hologram generation, I conducted a project for making AR navigation helmets. So we make a scenario like some food delivery drivers are bringing food to somewhere. So, but he want to see the navigation while he is driving. So we make a AR navigation helmet with a hologram. So it can adjust the contents by the site according to the site of the riders. So we developed five techniques, and one is the computer generated hologram using camera in the loop to compensate and optimize the CGH. And another technique is real-time hologram rendering pipeline. So start from the 3D object, and it renders the hologram in real time with binocular. And we apply the wide field of view HOA lens here, and we are co-work partner May Display, make an across display for CGH modulation, and we design the projection optics for the hologram, and we build up together. So this is the prototype. I'll see you later for big picture. And this is a hologram compensation using camera in the loop called CITR method. So there is a HMD here, and we place a camera, and by projecting the hologram with HOE and the camera see it, we can compensate and compensate the hologram's distortion or color aberration like this by seeing the real image of the hologram. So this is the target, and the camera observe it, and you can see the distortion and color aberration here. And by using camera in the loop method, we we adjust the original target like this, then display again, you can see the corrected image here. And another thing is CGH rendering pipeline. So we connect with the Korean navigation software API server and get the contents of the navigation, like an arrow or the distance or the line or something like that. And we make it 3D and render it in real time using the Unity game engine. And with the Unity game engine, we place the contents appropriately according to the rider site, and we render it with the binocular camera. And this is the rendered result. So this is a normal 3D scenes, and this is the real-time converted CGH. And this is a propagation simulation of the navigation contents. And as you can see, it is as propagated, the multiple signs, multiple information of the traffic can be focused according to the distance. And this is our projection unit. So this is one side of the projection unit, and here placed the RGB laser or LED laser diode source, and there is a projection unit here, like a lens or something like that, and here placed the LCOS display amplitude time modulation, and this is the final prototype of our AR navigation helmet. So each projection unit is placed here. They project the hologram CGH to the HOE lens, both sides, and this converged to the rider's eyes, rider's pupils. And also there places LCOS SLM with 4K resolution, and there is a board here, and we display the CGH with a mini PC. So the mini PC sends the CGH to the operating board, the operation board driving the SLM and LDs together. So it has a 360 hertz by using just one SLM field sequencing color technique. So it switches the LDs and LDS colors and SLM's hologram according to each color channel. So we analysis the prototype of the AR navigation helmet. So it started from the 1 diopter and like far away, and very close 4 diopter, like 25 centimeters in front of the rider, and we analyze the gradient pattern and for width maximum, and they focused each distance as we designed the depths of the CGH. And by utilizing the HOE, the great benefit is we can have a very large field of view. So like vertically 37 degree and horizontally is 72 degree. Total about 80 degrees total or diagonally. So we can have a very large field of view AR helmet. And we prepared the 2 types of scenario. One is kind of virtual riding simulation using Unity, and we capture the displayed AR navigation contents with the camera module, and also we can actually wear the HMD. So we make a virtual cockpit, and so we can get the traffic information of the navigation real time, and we can display it according to the appropriate distance. So this is the first part of my project, and another is about the avatars for the extended reality. So the project is generating photorealistic avatar with 3D face scanner and drive the avatar by the sounds. So as I say something, the avatar follows the motions and lip sync as I said. So for the 3D scanning system, I used like a very conventional techniques. I think most of you know the structured light and photometric stereo. But I explain, structured light is exposing some designed patterns, like a grid pattern or some phase shift pattern or something like that with a 3D object. And then the pattern is reflected and distorted by the 3D geometry of the target 3D object. Then we can calculate it reversely, so we can obtain the 3D geometry of the 3D target, exposed 3D target. And another method is photometric stereo. So just place the camera normally to the surface and expose the light according to the various direction. Then you can obtain the very different reflection image by the direction of the light sources. And by calculating the reflection direction, you can get the normal map of the 3D surface. So it is a very good solution to represent the like a human texture or human skin texture or something like that. So it is a good solution to capture the very photorealistic 3D faces for the avatar. So the first prototype is photobooth type 3D face scanning system. We make a kind of cube, 2 meter size cube here, and place the planar light source with 6 direction, plus x, minus x, plus y, minus y, and plus c, minus c. And this is the 6 captured image of photo of the according to the planar light direction, and this is a captured normal map. As you can see, the very fine grains of the human skin textures can be captured. And this is me. This is my 3D face captured with the photo booth. As you can see, my some dots or skin textures are, yeah, it is very realistically captured. And also, but I think the photo booth type is quite large to using for the commercial application, and so I try to make it more smaller and modularization. So this is a desktop type 3D face scanning system, but it doesn't have the photometric stereo. It just only have the camera, and inside the embedded board like just Nano, and this is the DRP project to project the structured light very fast, like 50 times in 1 second or more. And this is a scanning module with a camera, projector, and embedded board. And each embedded board calculates the 3D geometry and high resolution image of each side. And so it's just one of the module. And if you utilize the very multiple module according to your purpose, each module calculate the captured each side, and the master module combine it and make a 3D object. So for the scanning, for the real use, I combine the 4 modules, like left and right, and front top and front bottom. So we make a 4 module with a desktop type 3D scanning system, and it can be placed on this size of the desk too. So it is better to move, or it is better to place like everywhere you want. And this is the captured result. And maybe you can compare the previous result with this one. So it captures the 3D object very fast. So even though it does not use the photometric stereo, I think it is better than the previous result. And this is the scanner operations with the slow motion. So 1 second. In a 1 second, each of the 4 scanner captures the 50 structured light and the image simultaneously. So it is triggered by we make the trigger board and it's controlled each one. And it has a very short shutter speed, so it does not overlap or it does not hinders each other scanning. Oh. Oh, okay, sorry. Yeah. So, did you see my face? And this is a scanning operation with a slow motion. So, and this is the avatar generation pipeline. So first we scan the 3D face. Its reconstruction is very short, less than 2 minutes. And it has like a 20 million point cloud geometry, but if you want, you can gather more. And the texture and normal map is a 2K by 2K resolution. But if you want, you can replace the camera with the 4K resolution, but it has the trade-off with the capture speed. So I think 2K is very optimized scan for the commercial 3D face scanning system. And after scan the original object, we fit the 3D face with the template face model, and it can be moved, like it have a face shape or moving shape, blend shape, something like that. So we fit the template model with the scan data. Then you can make a motion with the scanned face. And we apply the deep learning sound model. So if I say something, they make a shape parameter of the face, and the face is moving automatically. And after that, we convert the fitted model to the game engine avatar. We use the earlier MetaHuman, and it's almost automatic, but when we scan when we move our scanned face to the earlier MetaHuman, sometimes there are some misaligned, like end of the lips or something like that. So a little human-based correction may be needed. So this is the result. No sound? Okay. So when I say 안녕하세요, he follows 안녕하세요. And also by utilizing the earlier, we can capture the whole light field of the 3D capture system, and we can print it with a hologram. So this is the 3D light photos, and like K-pop idol entertainment, very like this. So I want to take a 3D photo of the aespa and print it with a hologram, and I want to have it. That's my hope. So this is my conclusion. For the extended reality, I conducted 2 projects. So to represent the project, one is for the HMD. I made the augmented reality HMD for the navigation purpose. The benefit of the AR HMD is you can adjust the contents according to the sight of the user. So if you're driving, you want to see further, or if you want to see information, you can want to see the information very closer in front of the eye. But holographic AR HMD can do that. And it is relatively lightweight and has a wide FOV by utilizing the HOEs. But it still needs the power and data transfer cable, so it is quite annoying by attach the cables. And we try to make the FOV very large, so it is a very small iBox. This is kind of very killing point. So it's a kind of semi-Maxwellian, so it is a very small iBox. This is not good. And also, I made a 3D face scanning system. It is very high speed, and it can capture your face very photorealistically. And also, we built the avatar generation pipeline, end-to-end pipeline. So from the capture and driving with the sound and converted it to the game engine, so you can use it for the metaverse. But I think this is a very conventional method. So nowadays, the 3D AI is very popular. But I think still the quality is better than the kind of AI 3D reconstruction. But it is very convenient, just one shot and then you can get the avatar generation. So compared to the AI generation, it is very inconvenient. And sometimes it has some awkward facial movements. So it is hard to represent the very complicated motion of the face with artificial intelligence. They should be improved. And for the future, I conducted the two projects separately, but I want to combine them, and by utilizing the AR HMD, I can see the avatar of the very famous singer or something like that. So this is the end of my presentation, and thank you for listening.
So thanks for exciting talk. So I think we can open one or two questions. So any question we have interesting for the talker? No? Yeah, please.
Thank you. As for the navigation system, I think the unfocused image could be an obstacle for recognition of a load or other situations. So is it an issue, or how evaluate the issues?
So you mean the unfocused image can be hindered the rider's eyesight, right?
Yeah.
Yeah, maybe it's right, but compared to the conventional HUD system, all of the contents are placed on just one plane, and they never adjust, or they always hinder the sight of the right drivers. So the unfocused image may hinder, but it is better to the conventional HUD. Yeah.
Do we have another questions? In fact, I have several questions here. So the first one is because right now you propose a printed HOE for the solution. So I'm interested to know, do you have any issue about if the environment temperature is changed? How the hologram material will be also changed. So do you have any idea how can we further adapt for the HOE, which is very sensitive to the environment?
Right. So our lab is on the 8th floor. So when it was we make a digitally designed HO printer at the 8th floor's lab, but there's some vibration, or it changed the temperatures by the outside temperature. So the quality is actually not good. So we make a room at the underground of our building, and we make another printer at the underground laboratory. Then it is very stable. So you're right, the printing condition is very affected by the outside environment. So I think it is better to build your HO printing equipment that like underground or something like that. Yeah, that is important.
Okay, thanks. Do we have any questions here? If not, I think we can thank the speaker again.
Thank you. Thank you for the direction.
So our next talker is coming from the Yangming Jiao Tong University, and the speaker should be Yunan Liang. So Mr. Liang, you are here? Oh yeah, thanks.
Okay, so hello everyone. My name is Yuan Liang, and I'm from National Yangming Jiao Tong University. And our research is about diffractive light guide using holographic optical elements for see-through near-eye display. And so for recent years, the big technology companies like Apple, Google, Amazon are working on develop the AR MR system, the near-eye displays, because they think it's the future to replace the smartphone, just like the smartphone to replace the television. And in the AR and near-eye displays, there contain a lot of technology, like the head tracking, the sensing, mapping, or the image. And our lab is working on the hologram for years, so we decided to use our knowledge to work on the waveguide, to use the HOE to work as a coupler on the waveguide. So usually our waveguide contain a micro display to display the image, and the image will go through the projection lens and go into the first coupler, VHOE, and the coupler will diffract it through the TIR and go to the out coupler, then diffracted the image into the human's eyes. Okay, so in our research, we just wondering because there's two type of the diffraction. Like one is the refraction type, and the second is the transmission. So I think I will present the two types of the waveguide by the diffraction characteristic and color performance to see which is more better for the AR glasses. So first, for the refraction type HOE, here is the diffraction efficiency, and you see it's complicated, but we only have to notice two important parameters. One is the phase mismatch, and the second is the coupling constant. And these two shows that when you incident with the different angle to the HOE with the same wavelength, it will have different diffraction efficiency. And also because the coupling constant can present the coupling strength, so we choose to use the N1 and in the coupling constant to present the strength of the coupling constant. And you'll see that the refraction type VHOE, when the coupling constant growing up, then the incident angle tolerance will be larger, and that's great. And after that, we can just combine every incident wavelength. It will have different incident angle tolerance here, and will come to this Sprague degeneracy figure. And you'll see that every incident angle will have different band with the wavelengths, and with different incident angle we will change. So the refraction type hologram will have different color performance at the different incident angle. And for the transmission type, the diffraction efficiency is the chi-square function. So you'll see the different position of the incident angle at the figure will have different diffraction efficiency. And as the coupling constant growing up, it will have the chi-square function. So when we combine all the figure together and see the Bragg degeneracy, we'll see at the different at the negative incident angle, the diffraction efficiency will be fragment. So that causes when we see the final image, we'll see the image is not continue at this angle. And after that, we have the diffraction efficiency. We can use the spectrum and the X bar, Y bar, Z bar for human size to calculate the color performance of these two types. So, and we can see that the transmission type, because of the chi-square function, so we put the blue color block and the green, red and the white color bar, the image will be so fragment, and then the whole image will not be continuous. And for the refraction type, that will be more continuous. It will provide a more continuous image, and so at the end, that will say that the refraction type VHOE demonstrate better color performance and a continuous field of view. So that's more suitable for the AR display.
Okay, thanks for speaker. So do we have any question for speaker? I think we have many times can have many questions here. Do we? So I have several questions here. So we know for the HLE, you try to analyze the refraction type and the transmission type for different about performance. But we also need to consider about what the possible data index variation within a different wavelength range.
Yep.
So in your study, do you see that if no matter is a transmission or even a refraction type, do we have any conclusion or even you have idea about what kind of the best refraction variation will be best for this kind of application?
Refraction index. You mean for the?
I mean.
Okay. I mean maybe because the refraction type the band will get wider than the delta n going bigger. So maybe for the refraction type, it will better for as large as possible. But for the transmission type, because it's the chi-square function for the diffraction efficiency, so maybe different wavelengths, we incident with different wavelengths or incident angle will have different the best delta n. Yeah, so maybe for the material for we really to use on the AR glasses, it's better. The refraction type VHOE is better.
Do you have any question here? No? So I still have some. Yeah.
For the use for AR glass, it is important to you reported the diffraction efficiency, but also important is the transmittance of the incident light.
Yeah.
We compare about the transmittance.
Okay, so for our material, we are using the bifold HX200, and the transmittance is about probably 90%, and it's a good see-through material for us for now. Yeah.
That transmittance doesn't change between the transmission type and the reflection type.
Sorry.
You compare the reflective type and the transmission type.
Yeah.
Volumetric
Oh, yeah.
holograph elements. There's no difference between them.
So
Transmittance doesn't change between transmission type and the
so
reflective type.
you mean two types of
Yes.
will have different transmit? I think yes. Yeah. After we recording, you will have same transmittance. Yeah, it's about 90%. Yeah.
Okay, thank you.
So we have questions here.
For AR glass application, there are many applications such as LC COS, LBS, DLP, or micro OLED. What's your benefit of VHOE compared to those technology?
I think so. I think you mentioned is about the micro display. Micro display panel in our system, right? Different, and for the VHOE, you can see that the different incident angle will have different wavelengths. So when you have wider spectra from the panel, you'll get a wider field of view in the end. But it will also cause the color gamma will be limited because the wavelengths at the here and here is much more different. So the final you cannot get a uniform color performance in the final image. So I think this curve is based on the angle when we record the VHOE. So I think your answer will also have to consider the recording condition to just consider whole system together will be better. Yeah, and yeah.
Yeah. So, do we have any questions? We still have time, right? Okay, I just follow the same question from the question. So I think the question here should be focused on because for different display solution, we have different kind of wavelength spectrum.
Yeah.
So I think the question is for this kind of VHOE, no matter it's a transmission or even a refraction, what kind of wavelength condition you will be prefer? You will be prefer very narrow bandwidth, or you want to display with very broad spectrum?
So I think the broad spectrum will be better for the uniformity for the whole field of view. Yeah. Yeah, in both type.
Yeah. So if no questions, so let's thank the speaker again.
I'm Hirotsuga Yamamoto from Utsunomiya University. It's my honor to chair the next two papers. Okay. Let us continue with the next contributing paper presentation. The speaker will present an optical simulation and optimization approach for suppressing diffraction in automotive head-up displays, aiming to improve image quality. So the paper is titled Background Image Quality Enhancement via Diffraction Suppression in Automotive Head-Up Displays. The authors are YW1 and so on from National Taiwan University.
Thanks for the introduction. And good afternoon, everyone. And thanks to for your time this afternoon. I'm Yuan Wang from National Taiwan University, and it's my honor to have this opportunity to speak here. In this presentation, I would like to talk about background image quality enhancement via diffraction suppression in automotive head-up displays. So this is my outline. First, I will use a mindset called NSDB to analyze our study. Then, I will talk about the cause of diffraction and the simulation model. After that, I will look into the results and have a discussion. Lastly, I will conclude with some key points as an ending. So today, I would like to share a mindset that we use in our research, called NSDB. So first one is need. We need to reduce the light diffraction that comes from the structure of curved transparent displays. And the second one is the solution. We design the diffractive optical elements, or DOE, to suppress the light diffraction by using the phase modulation. And the third one, differentiation. Unlike traditional software method, our hardware method requires no additional image post-processing after applying the DOE, which is a real-time optimization. And the last one, benefit. After the optimization, the energy share of non-diffracted light can be increased by around 22% in terms of efficiency. So now please look at the original reference image at the left side. After the diffraction, you can notice the middle one's image becomes darker and unclear. But after our optimization, we can restore part of sharpness and brightness. So first of all, we need to figure out the cause of diffraction. The source is the electron distribution in curved transparent displays, as you can see in the picture of the left one. And the middle one is a corresponding enlarged view, where each white block represents an aperture. Since the size and the spacing of the corresponding structure are on the micro scale, it can cause a clearly diffraction effect, resulting in a blurred vision, as you can see in the picture at the corner. So in our research, we will simulate the curved transparent displays as a windshield of a vehicle. Since each vehicle has different windshield design, we performed simulation by using the built-in HUD model in the ZMax software. And the extended polynomial of representation of the spherical surface was also implied. The meaning of each parameters in the equation are shown below. Also, the summation term describes the surface variation along the x and y directions. This adjusts the spherical part of the surface. However, here comes a new issue. The built-in HUD model in the ZMax software is a triangular mesh surface, as what you see in this picture. But what we need is a surface that is described by an extended polynomial. So that's why we have to do the surface fitting. By using the MATLAB program to read the STL file and preallocate memory for vertices data, we can extracting all the vertex data and save the data in the mesh structure and finally complete the fit surface function. So at this point, we can finally obtain the polynomial parameters that can be used within our research. So with the polynomial parameters obtained, now we can look into the optical path. So we set a point light source that emits toward the displays first. Then the light will travel through the electron distribution layer, which causes a phase change. Then it will travel through the gas subject of curved transparent displays. After that, it will go through a thin lens for focusing to simulate the lens of human eyes. And finally, it will reach the sensor to simulate the retina, where the light field is calculated and investigated. So this slide shows the method that we use to simulate the light propagation. We use the Fresnel-Kirchhoff diffraction formula to describe the light propagation between planes, as you can see in this equation. And we use a two-step diffraction propagation technique, which breaks down the complex propagation path into the multiple segments of free space propagation. This makes the simulation take less time. Moreover, because the curvature within our sampling range is small, so we can assume that the light propagation is uniform. As a result, the impulse response depends only on the distance between the planes, and we don't need to account for the surface variation along the x and y directions. This also makes the simulation take less time. So with the corresponding simulation propagation method, now we can finish the optical simulation. Starting from the point light source, we simulate the light field undergoes the electrode layer, where the max turn is a binarized matrix defined as the electrode distribution, and the phase turn indicates the phase shift contribution. After that, the light will go through the gap substrate with the first convolution-based propagation, and it will travel through the DOE for phase correction, followed by the second convolution-based propagation and the thin lens, and finally undergoes the third convolution-based propagation before being focused onto the sensor. So with the corresponding optical simulation, we can obtain the complete light field information at each stage along the whole optical path. This allows us to evaluate the system's performance and identify the diffraction effect. So after the optical simulation, we can obtain the energy distribution with the diffraction effect at the sensor, as you can see in the picture on the left one. To optimize the outcome, we first define the target light field by removing the higher order diffraction component. In addition, we introduce the constraint based on the conservation of energy by linearly adjust the energy of non-diffracted light to measure the total energy of the diffracted light field. Now we can obtain an ideal target light field that without the diffraction effect, as you can see on the picture in the right side. So with the ideal target defined, now we can finally jump into the DOE design and optimization. We use the phase retrieval algorithm to update the phase of the DOE. At the core method, we use the simulate annealing method to prevent the system from stuck in the local optima. And the right side is the flow chart of our key steps in our algorithm. So first, we will randomly adjust the phase of the DOE and calculate the corresponding current light field, then compare it with the target one. So to judge the result, we introduce a new parameters called cost function, which is defined as the difference between the current light field and the target one. So if the result improves, we will accept the phase change right away. But if not, we might still accept it with a certain probability, which depends on the current temperature, also a key part of the simulate annealing method. So after this step, we will gradually decrease the temperature, lowering the probability that accept worse solutions, and repeat the whole optimization process until the convergence is reached. So here's another question. To see if our algorithm has converged, we introduce two new convergence conditions, the optimized rate and the immovable rate. The optimized rate is defined as the numbers of improved or maintained updates divided by the total numbers of DOE updates. And the immovable rate, on the other hand, only considers a ratio that maintains the current performance. So once both of these conditions at the corner of this side are met, it means that most updates no longer improve the performance of the DOE, which indicates the convergence. And the picture shows the cost function curve of our algorithm approach convergence too. So this figure further confirms that the convergence has been achieved. So after finishing the optical simulation, now we need to quantify the optimization effect. To do this, we introduce another new diffraction parameter called diffraction ratio, which is defined as the energy of each order diffraction to the total incident energy. And in this page, we first look at the zero order diffraction ratio because it best represents the efficiency of DOE. And then we compare the energy distribution before and after the optimization at the same time. And as you can see, the zero order diffraction ratio has been increased by around 22%, proving that the DOE is highly effective. However, you can also notice that the diffraction light intensity along the X and Y directions appears to be enhanced as well. So we can take a closer look at this point in the next page. So in this page, we investigate the energy redistribution because of the optimization. We analyze the intensity of point spread function, or PSF, along both diagonal and y-axis cross-section before and after the optimization. So as you can see, the zero order diffraction ratio has been successfully enhanced. and the diffraction light intensity along the diagonal path has been successfully suppressed. However, the y-axis cross-section profile also shows the increasement in the diffracted light intensity, as you can see the picture right here. So it will be our main future work. So it's time to make some conclusions. With a well-designed DOE, the diagonal diffraction in the curved transparent displays can be successfully suppressed by using the phase modulation. And the energy share of non-diffracted light can be increased by around 22%. This not only enhances the useful signal, but also suppress the ghost image. And speaking to the future work, we will focus on handling the remaining diffraction effect, improving the manufacturing compatibility, and reducing the computation simulation time. So this is the end of my report. Thanks for your attention. If you have any question, I'm willing to try my best to answer. Thank you.
Thank you. Thank you, Vincent. And we have also plenty of time to question. Do you have any? Takashima.
Thank you very much. So this is a very interesting talk. And I have one question. So now, the goal of this work is, basically suppress higher order diffractions, like plus minus first order, for example. Correct?
Sorry, but can you say that again?
Yes. The objective of your work is basically suppressing plus minus higher order diffractions.
Yes.
Right. So then, I think there are two scenarios, right? One is plus minus first order, higher order is suppressed. Second scenario is now plus minus first order is rediffracted towards zeroth order. So which actually is working is a working operational condition, operational principle?
So you are meaning the higher order diffraction suppress how the DOE redistribute this energy go to the zero order diffraction ratio.
Right.
Also, this is use the phase modulation, and we use the algorithm that please let me to change to this page. So we change the phase of the DOE, and we every time we randomly adjust the phase of the DOE, then we will calculate the corresponding current light field and compare the zero order diffraction ratio to see the diffraction ratio, the variation of the diffraction ratio. So if the diffraction ratio increase, then we will accept it right away. But if not, we will just to delete the change of the DOE. So we just use the retrieval algorithm to find the best optimization answer to the DOE's phase correction. Yeah.
Oh, okay. So then the other question, same question, but in a different ways now. How that phase profile look like after optimization? How the phase of DOE look like? Is that the inverse of electrode pattern, or how that look like?
Sorry, but I can't understand.
Okay. Do you have any plot of how phase modulation profile
sorry, but in the light propagation simulation, we just use the matrix in the MATLAB program to simulate, and we don't just save the data about the simulation path. So
understand. But did you plot that profile?
The profile, do you mean the energy distribution or
no,
the phase distribution?
Phase distribution.
We have saved the phase distribution, but we didn't put the phase distribution on this presentation file. So if you are interested about that, maybe I can just provide you after this presentation.
All right. Thank you very much. That's very interesting. Thank you.
Thank you.
Any other question from audience? I'm curious about this lens and sensor. Would you explain in detail for the focal length of the eye model and the diameter, and most importantly the distance from the object to viewing distance?
The distance between the planes and the human eyes. We set the distance is about 75 centimeters because of the mean distance between the windshield and the human eyes. And we just and this is adjustable. So if you have another parameters, then we can do the same method about the simulation and obtain another DOE's phase distribution.
And the iris size?
Iris size. Oh, means the iris size about in our sampling range, we sample the iris size is about the radius about 1.75 micrometers. So that's 1.75 micrometers. So there's a little very small parameters. We didn't simulate the sampling range in a such big range. Yeah.
Oh, but I'm curious about the eye model.
Do you mean the distance between the lens and the retina?
The lens size is 0.17.
1.75.
1.75.
Yeah.
Very small compared to our eye.
Yeah. So we just focus on the central of the human eyes. The
focal length. How about the focal length?
Sorry, but
focal length of the lens.
Means the distance between the lens and the lens. We set about 0.28 centimeters.
28.
Yes.
Our eyeball has mainly in the standard case, focal length is set 17 millimeters or so.
Okay. Yeah. The parameters are changeable, and it is not affect our simulation method. So it is suitable for these parameters, and we can search more reference data and change the parameters that we use in our human eyes contribution or human eyes the parameters. So thank you for your information, and we will keep improving our parameters about the simulation environment and the parameters. Thank you.
Yes. And the F number is set. F8 is mainly used for the standardization.
Okay. Thank you very much.
Oh, it's just time. Okay. Good. Thank you for that questions. Okay. The next presentation is a user study investigating visibility improvements in augmented reality by applying both blur and color enhancement to virtual characters. The paper is titled by Blur and Color to Improve Visibility of Virtual Characters for AR Display. The authors are Yuta Machigashira, Haruki Mizushina, Munekazu Date, and Kenji Yamamoto from Tokushima University and also Shinshu University and Tokushima Bunri University. The speaker is Mr. Yuta Machigashira. Let's welcome the speaker.
Thank you everyone. So let's start. I'm gonna start my presentation. I'm Yuta Machigashira from Tokushima University from Japan. Today I'm going to present about utilization and visibility of blurred characters and colored characters for AR display. So here is today's contents. So first of all, let's start from the background. In recent years, technologies such as VR, AR, and MR have been attracting attention. And the main application of these technologies are business, entertainment, medical care, and so on. However, the stereoscopic display method based on the binocular display still has problems such as the eye strain, divergence accommodation conflict, precision limitations, and so on. And many studies are being conducted to reduce these problems. In this situation, we focused on the visibility of contents in AR. We assumed AR navigation and through visibility of AR contents is very important for users. For example, showing the name of buildings or showing some announcement for AR navigations like this picture. When considering the application like this, we thought that the visibility of AR contents is very important. So we set our purpose as analyzing the visibility of virtual characters and finding the way to improve the visibility for AR display. Previously, we investigated visibility of adding blur to the virtual characters and the visibility of changing color of the virtual characters, like this. Left one is blur added AR, so blur is added to the stereoscopic display like this, and the right one is the color added AR, so this is the gaze point, and the gaze number is changed to from white to red. But however, we didn't consider adding blur and changing color at the same time, so we investigate it this time. Next is about the sensory test method. Okay, this is the test items. One is the blur added AR, and the other is the blur color added AR. This is the blur added AR. When the gaze position is not settled, there is no blur. There is no blur like left images. And when the gaze position is settled, a blur is added to the characters in periphery of gaze position, like right image. So the first image is red one, and change to right image. So like this. Oh, sorry. Image was changed like this. And this is a blur color added AR. When the gaze position is not settled, there is no blur and there is no color like left image. And when the gaze position is settled, a blur is added to the characters in periphery of gaze position, and the color of virtual characters at the gaze position are changed from white to red, like this right image. So the image was changed like this. Blur is added and color is changed at the same time. And this picture shows the equipment we used in the experiment. We used stereoscopic display, half mirror, slit, and chin rest. And this figure shows why we used that slit. This is a side view, and there was possibility that subject can't observe the virtual number as we expected because of the height of their eyes. It means that virtual numbers can't link to the real object as we expected. So we use a slit to make the height of their eyes same as we expected. And this slit was removed after adjusting the height. And this figure shows the viewing distance of equipment. The closest real object is about 0.5 meters, and the farthest one is around 4.3 meters. And this figure shows how virtual characters are displayed. Now, red numbers and red lines are virtual images, and the black numbers indicates the real object. Virtual numbers are displayed at the same depth as each real object, like this. And the previous research pointed out that when the disparity of 3D images is fixed, depth perception error occurs due to the differences of the interpupillary distance of the subject. So we measured the interpupillary distance of each subject and calculated the disparity of the virtual numbers based on the interpupillary distance of each subject. And next is the procedure. This is the observed scene, but please note that this photograph is for illustration purpose and not actual observed scene by subject, because the actual image is a stereoscopic display. Stereoscopic image. And yeah, from the procedure is the first subject saw the blue alphabet that has no disparity. Now it's A here, blue alphabet. Now it's A. So, and second, subject searched the one real object with the same alphabet printed on the blue alphabet from 10 real object. Now blue alphabet is A, so subject have to find A from the real object. After that, subject pressed the same arrow key as printed on the specified real object. So here is A, and the down arrow is printed on the A, so subject pressed the down arrow keys. And subject pressed the virtual 4-digit number linked to the real object with the another keyboard. So it's now it's 8245. And the time taken by the subject to place 4-digit number was recorded with millisecond precision. And the subject did 120 trials for blur edit AL and 120 trials for blur color edit AL. In addition, 60 trials of the 120 trials were trials without any virtual changes such as blur and color, and the remaining 60 trials were with virtual changes such as blur and color. In this study, we assumed that the moment subject press the arrow keys is the moment the subject gazes at the real object, and we changed the blur color situation of virtual images at the moment subject press the arrow key to simulate the gaze response display using eye tracking. And the time between the input of arrow key and the input of first digit of virtual number was defined as response time. Mistakes made by subject was excluded from experimental data, and a 5-minute break was provided for every 60 trials. And this is the subject information. 9 people participated in this test, and they were all males. And some subjects were corrected with glasses or contacts, and all subjects have normal stereoscopic display, stereoscopic vision. And next is about the result. The result is shown on this figure. The blue triangle shows the response time of blurred added AL. Blue one is blur added AL, and the red circle shows the response time of blur color added AL, and the x-axis shows the response time, and the y-axis shows the viewing distance of real object. According to this figure, the response time of blur color added AL were shorter than those of blur added AL in some cases. The orange shows that result, but just one opposite significant differences was observed at the real object number 1. This is the opposite significant differences. And this is the result of the questionnaire. We asked which method was better for you to the subject, and we allowed them to give the tie ranking answers. As a result, one subject answered both of them was good, and the others answered blur color added error was better. So I'd like to talk about discussion from here. My hypothesis is response time of blur color added AR will be shorter than response time of blur added AR. The result indicates that the response time of blur color added AR was shorter, but there is one opposite result. We presume that the reason of this is the illuminance of virtual number. Here is the opposite one. The virtual color of virtual numbers that subject gaze at always white on the blur added AR, but the red on blur color added AR. So the luminance values of the virtual numbers are different from between the blur added AR and color added AR. So we measured the illuminance value of the virtual numbers. The white was 40.69 candela, and the red one was 31.84 candela. And the luminance difference between the red and white in this test was 8.85 candela. So we presume that the subject perceived the difference of the illuminance between the white and the red virtual numbers. In addition, the background of displayed position of virtual number linked to the real object number 6 was darker than other numbers displayed position because of the shadow. So as a result, we presume that the significant difference opposite to our hypothesis was observed in response time of real object number 6. So final one is conclusion. We conducted sensory tests for visibility of blurred virtual characters and colored virtual characters. The results showed that blur color added AR is better in analysis with response time, and the blur color added AR is better in analysis with questionnaire. Therefore, we presume that blur color added AR is more effective to improve visibility. However, we believe that further experiments are needed to verify the validity of our hypothesis in more detail. That is all of my presentation. Thank you for listening.
Thank you. Yeah. One short question. Yeah. Okay. Hi. Did you investigate the change of the changing the ambient light?
Ambient light.
Yeah.
What?
So yeah, when the room light is darker, then result may be changed.
Yeah, I think so you mean the ceiling light?
Yes, ambient light. Yes.
Okay. Yeah, it might be effective to our result. So it is difficult, but so if it darker, it will
darker is okay.
Darker is okay. Yes, yes.
But for the outdoor use, very bright.
So you mean the illuminance of the light, seeing light
background?
I didn't measure it in actual.
But it's very important.
Yes, yes, exactly. So yeah, I measured when I back to our laboratories.
Yes. Okay. We don't have time, so thank you much, Gasha-san.
Thank you.
Yeah, I think we have last talk in this section. I'm coming from the Center of Optical Research and Execution in Japan. So the title is the see-through error image display with adaptive eye box systems.
Thank you for taking your time. AR display has been expected to create new applications such as digital signage. And today, I'd like to talk about the novel iBox system for such an AR display. The title of the presentation is See-Through AR Imaging Display with Adaptive iBox. I'm Naru Skura from Utsunomiya University, Japan. These are the contents of today's presentation. At first, I'll talk about AIRR, aerial imaging by retroreflection, and then the combination of AIRR and VR optics. I also show the example of the previous research of the combination of AIR and VR optics. Secondly, we think previous research has an issue about iBox. Thus, I'd like to show you a proposed structure as a countermeasure. Thirdly, I show the experimental result, and finally, I'll show the conclusion of the presentation. AIRR is one of the most promising technologies to achieve aerial image and is expected to create new applications. This is a basic structure of AIRR. This is a display, reflective polarizer, and equator wave plate, and retroreflector. Every acronym is shown at the bottom of each slide. Please take a look. The display emits the light, and the light reflected at the reflective polarizer and retroreflector, and then goes through reflective polarizer and creates the aerial image in front of the user, so a user can see the aerial image. The function of the AIR optics can be considered to be copying the light to a symmetrical position as a reflective polarizer. This creates this as a symmetric position. Similarly, see-through AIR can be realized as shown as the light figures. With this configuration, the light emitted from the display goes through the reflective polarizer first, and then reflected the retroreflector and reflected as a reflective polarizer, and creates the aerial image in front of the user. At the same time, user also can see the real scene behind the reflective polarizer. Recently, the combination of AIR and VR optics also has been proposed. Instead of just placing the display here, to display a combination of display with VR optics put here. In this case, we can consider that iBox itself is copied at a symmetrical place as a reflective polarizer. But note that because the user's position is not symmetrical, user can't see the virtual image because virtual image is created as a behind the user. So optics should be modified as shown as the right figure. When the display is located away from the VR optics, virtual image is also located in front of the user. The feature of this optics is user doesn't need to wear headset of VR. Therefore, users do not need to be conscious of wearing the headset, nor do they feel its weight. This feature has a significant potential for developing various new applications such as augmented surgery using XR image. Here, I'll introduce 3 previous research of the combination of AR and VR optics. The first previous research is an introduction of the combination of see-through AR and VR optics from Utsunomiya University in 2018. The left drawing is the original one from the white paper. The right drawing is the modified conceptual one. Owing to see-through configuration, the virtual image can be seen in the real scene. The second research is the combination of non-see-through AR and VR optics from Nikon in 2024. This VR optics is optimized to achieve larger eye box, 50 mm diameter, and long eye relief, 500 mm. The larger eye box and long eye relief enables users to see the virtual image easier. They have also proposed 2 concepts of applications. One is collaboration in real and virtual space. The other one is non-contact private viewing. This means only one person at a time can see the virtual image. Thus, security usage can be considered. The third previous research is a combination of dual SMAs. SMA means slit mirror arrays and VR optics. While the whole system is so too bulky, a user can see the same virtual image as a position as in the original position, owing to dual SMS copying iBox twice. As shown previously, there has already been a few unique proposals using the combination of AR and VR optics. However, we think this has a big issue that users can find the appropriate viewing position immediately. As I mentioned, Nikon has already proposed 50 mm diameter iBox, but we think it's still insufficient. Additionally, iBox positioned in free space without guidance. This is also the cause of it. To address this issue, we introduced a novel conceptual iBox system named the Adaptive iBox System. Our approach is that iBox itself moves toward the user by using an eye tracking system. When eye tracking system finds the user's position, iBox is moving toward the user. The key question is how to move the iBox. I'll explain it from the next slide. To move the iBox, our approach is placing the light shift optics between VR and reflective polarizer. The light emitted from the display shifted at this 1D optics. And eventually light goes through the position of copying the symmetric place. As a result, the iBox is shifted and the user can see the image as a different position from the original iBox position. To show the concept, we evaluated using 1D light shift optics in static condition without eye tracking system. Static means 1D optics changing manually. Regarding 1D optics, PBPDG, punctulatron Berry phase diffraction grating is currently a well-known device, and we choose this as 1D shift optics. So I'd like to provide a supplementary explanation about our PBPDG here. PBPDG is a static diffractive device with periodical aligned UV-cured liquid crystal molecules in 1D direction with half lambda retardation like this. This can shift lights in a 1D direction depending on angular polarization state of incident light. If PBPDG is designed that right-handed incident light shifts to the right, then left-handed shifts to the left. Note that handedness reverses after diffraction. This is actual design of experiment. BR optics is placed about 2 millimeter up. In this time, the PBPDG is used as 1D optics like this. This is actual design of this experiment. VR optics is placed about 2 millimeter upward from the display, and the PBPDG is placed about 30 millimeter upward from the VR optics. The light from VR optics is shifted by PBPDG and reflected at the reflective polarizer, then reaches toward the user. Note that position of virtual image also is shifted by PBPDG. When iBox shifts to the left, then virtual image shifts to the right. The pitch of our PBPDG about 4 micrometer, thus approximately diffraction angle is 8 degrees and 4 millimeter iBox shift is expected. Using the experimental setup mentioned previously, we evaluated the shift by the camera. The background photograph is located at 40 centimeter away and from the camera, and red leaves photograph is at 30 centimeter away, and the yellow leaves photograph is at 20 centimeter away, respectively. The camera focuses on the yellow leaves photograph, and the LA image letters Utsunomiya University is at the same distance. The position where the clearest image is obtained by the camera is assumed to represent the center of iBox. Our result shows shift is approximately 6 meters when iBox shifts to the left direction, then the image shifts to the right, as I mentioned. The image is blurred presumably due to imperfectness of PBPDG's optical pitch and color aberration. Brightness of shifted image becomes low due to low diffractive efficiency. We think The result proves the concept of adaptive iBox system. There is a gap in shift value between theory and evaluation result. We re-evaluate as the next step. These are conclusions. We propose a novel concept of adaptive system for combination of AR and VR optics. This concept has a great potential to make new applications related to VR, MR, AR with the following features, and the result shows a gap between evaluation and theory, so we should re-evaluate precisely. Thank you for your attention.
I think because we already run out of time, so if you have any question, please reach the speaker directly. So we will have a short break, and we'll have roughly about maybe almost 10 minutes after we have a new section here. So we'll come to back again. Thank you.
一叠。
那要可以广播他一下，他有到，他刚刚有 arrive。
哪一位？
那个这个 June Park。
哦
Dr.
June Park。
June Park。对。
申请 May I kindly ask the next session chair, Professor Zhang Yu Park and Mr. Shanting Chang, come to the front. Chang.
这边倒数第二个，等到信用卡，所以就掉地上，所以可能。
哦。
这边有倒数第二个，感谢你。
好像已经报道了，知道了。不是他，是另外一个，就是这个是法尔是盖森的。他后来说他。
我想要找一下那个明天的这个时候2:10。都是社区去，今天有2:10。哦，林江2:10。然后这个我看有家是要请假。Do you want to update the presentation?
Yeah.